Current Limiting Circuits Part 5. In this series of videos I have presented several ways to implement an electronic circuit breaker to limit the current of a circuit, especially in case of a short circuit, without the need of a heatsink device. We have progressed from a simple circuit using two NPN transistors in Part 1 to two PNP transistors with jumpers to allow for the changing of the current limit in Part 2, or using an R-sense resistor to limit the current in Part 3, to a combination of BJT and MOSFET transistors in Part 4, all with the objective of limiting the load current as an electronic circuit breaker. They all followed two objectives. 1. Limiting the current by shutting down the circuit when the pass transistor, BJT or MOSFET, collector to emitter voltage, VCE, or drain to source voltage, VDS, reaches a voltage drop around 0.7 volts. 2. Avoid the use of heatsink devices. I finished Part 4 with a circuit where the MOSFET voltage drop from drain to source was not part of the current limit design, which could raise the need for a heatsink device. This went against the second objective, avoid the use of heatsink devices. Depending on the transistor package, there is a limit of how much power the transistor case can dissipate without the need for a heatsink device. For instance, the TO220 package, with a maximum allowed junction to ambient thermal resistance of 62 degrees Celsius per watts, and maximum operating junction temperature of 175 degrees Celsius, at an ambient temperature of 30 degrees Celsius, is 2.3 watts. The RSJ250P10, an AD2 pack case, is a surface-mounted version of the standard TO220 package, having similar, or better junction to ambient thermal resistance, depending on the PCB board layout it is attached to. However, considering that the power dissipated by a MOSFET is the product of the RDS on resistance and the drain current, the circuit presented can work, without a heatsink device, if we calculate the voltage drop of the MOSFET over the current limit as per formulas. Using the maximum RDS on of the RSJ250P10 MOSFET as 70 milliohms. So, we can run the circuit up to a limit of 5 amps, and not 13 amps, as it was presented in Part 4. Even though the MOSFET voltage drop from drain to source was not part of the current limit, the R-sense value, 0.07 ohms, in this configuration, starts shutting down the circuit when the current reaches 5 amps, with the MOSFET exceeding the 2 watts limit for only 10 milliseconds when it is shutting down, green line in the chart. In this configuration, we have to estimate how much voltage drop we want between drain and source so not to exceed the 2 watts limit, and add it to the drop on the R-sense resistor to reach the 0.7 volts limit voltage drop. In the case of the circuit presented, the 5 amps limit times the RDS on resistance of 0.07 ohms equals 0.35 volts, green line showing the VDS voltage drop. 0.7 volts minus 0.35 volts equals 0.35 volts, pink line showing the voltage drop on R-sense resistor to trigger the circuit. A 0.07 ohms R-sense resistor will limit the current to 5 amps, as shown in the picture, cyan chart showing VDS plus R-sense voltage drop of 0.7 volts. The circuit presented is what is called a load switch. A load switch is a circuit that controls the connection and disconnection of a power supply to a load. A load switch is comprised of two components. 1. The pass transistor. 2. The on-off control circuit. The pass transistor in the load switch can be a BJT or MOSFET transistor. A MOSFET pass transistor can be a P-channel or N-channel transistor. The picture shows a P-channel pass transistor, M1. An N-channel MOSFET pass transistor has the advantage over a P-channel due to a lower RDS on, resulting in higher currents and lower drop out of the drain to source voltage, consequently lower power loss and lower MOSFET heating. When using an N-channel MOSFET pass transistor in a load switch, the drain is connected to the power supply and the source is connected to the load. In order for the N-channel MOSFET to fully turn on, the gate-to-source voltage must be greater than the gate threshold voltage of the MOSFET. For that we need additional circuitry like 1. Additional power supply with a voltage higher than the gate threshold voltage, plus the main power supply voltage. In the picture, for a 10 volts gate to source voltage we need an additional 22 volts power supply. Most of the time this is not possible, or convenient. 2. A charge pump circuit, a kind of DC to DC converter, to increase the main power supply voltage above the gate threshold voltage. A charge pump can be as simple as a monostable voltage doubler. Here is the circuit with the charge pump in place of the additional power supply. However, the use of a charge pump requires a switching circuit, adding extra circuitry and the need for protection against noise generated by the charge pump. 3. A bootstrap circuit to pull up the gate to source voltage above the gate threshold voltage. The bootstrap circuit uses what is generally called a flying or floating capacitor. The capacitor is connected between the gate and source terminals of the MOSFET, boosting up the gate-to-source voltage above the power supply voltage. The design of the bootstrap circuit has some of the components of the charge pump, the capacitor and diode, but without the switching mechanism, usually an oscillator. This is the circuit I am proposing in this video. Warning must be provided for the design of the bootstrap solution. 1. The absence of the switching circuit, charge pump, to keep the capacitor charged, allows the capacitor to decay over time, reaching a point where the gate-to-source voltage is just enough to keep the MOSFET on, cyan line, with a high drain-to-source voltage, blue line, resulting in heat dissipation and power loss, green line. 2. That is why transistor Q1 is there. It senses when the drain-to-source voltage raises to about 0.7 volts, shutting down the circuit before the MOSFET heats up to 2 watts, green line. 3. While with the charge pump option the circuit can run forever. By specifying different values for the capacitor, C1, the bootstrap circuit can stay on longer as shown in the picture. 4. Many times, especially when used as a workbench load switch, the circuit does not need to stay on for a long period of time. That is when the second switch SW2 is convenient. To shut down the circuit and allow for the capacitor C1 to recharge, cyan line. 5. Extreme care needs to be taken on printed circuit board layout and the quality of soldering, to reduce possibility of parasitic capacitances, which may result in the capacitor draining faster than expected, resulting in the circuit staying on only for a few minutes. Believe me, it took me a while to have it working properly. Just look at my bad soldering job. Also, by having the capacitor C1, resistor R1, and diode D2 soldered very close to the MOSFET, the possibility of parasitic capacitances can be reduced. 6. As I have been presenting in these series of videos, the circuit would not be complete if I did not limit its current, like in a circuit breaker. So I added the R-sense resistor to shut the circuit off when a current limit is reached. The proposed design works like this. Initially, when the power is applied, MOSFET M1 is off, and transistor Q1 is the first to turn on, blue and red lines in the chart. This keeps MOSFET M1 off, green line, through MOSFET M2, pink line. During the time that transistor Q1 is on, capacitor C1 charges through diode D2, cyan line, reaching its final voltage of 11.3 volts, brown line, which is the power supply -1 diode drop. Then it is just a matter of turning the circuit on and off, using switches SW1 and SW2. As I have already mentioned, the circuit will decay with time and may shut down before switch SW2 is activated. If everything was done right, it should last for a few of hours depending on how much current it is being driven, as we will see shortly. The circuit built used MOSFET IRF540 for M1 and MOSFET 2N7000 for M2. Diode D2 was 12 volts, 1 watts, Zener diode 1N4742A. No R-sense resistor was included in this build, and during the tests, the circuit stayed on for more than 1 hour while driving a 12 volts, 2 amps automotive bulb. Before the previous circuit was built, a smaller one, using MOSFET 2N7000 for M1 and M2 was built. It stayed on for 6 hours without the R-sense resistor, driving a 40 mA current. This is the circuit running in the smaller window during this presentation. With the inclusion of a 2.2 ohms R-sense resistor, the circuit limited the current to 140 mA. The limit showing in the picture is for a 2N7002 MOSFET and not the 2N7000 used. This resulted in the circuit staying on no more than 2 hours while driving a 100 mA current. The R-sense voltage drop has to be taken into consideration now, as the voltage drop in the R-sense resistor added to the drain to source voltage shuts down the circuit earlier. This circuit has a peculiarity, which is why it was not used for the high current design. Instead of the diode D2, it used an NPN transistor, in a diode configuration. As it shows in the chart, and also in the note, there is a reverse voltage between the capacitor point A and the positive of the power supply, due to the charge of the capacitor. Any power supply voltage above 6 volts will compromise the transistor. However, it is a good circuit to be used in situations where the power supply does not go above 5 volts, like driving a 5 volts microcontroller, like the Arduino or Raspberry Pi. For a high current, high voltage power supply, in the final circuit, a 12 volts Zener diode was used. During the breadboard tests I used a Schottky diode 1N5817, which did not work. There is no reason for a regular 1N4148 diode not to work. However, in the simulation, the maximum current with this diode was 2.6 amps, with the capacitor draining down to 5.4 volts. With the Zener diode we get 5.5 amps, the circuit stays on longer, and the capacitor only drains down to 10.2 volts. That is why I opted to use the Zener diode. Another thing to consider for this circuit is that different load current will result in different on time. As we double the current, the circuit stays on for less time. less and less time on, like a timer, until it doesn't turn on at all, due to the drain to source voltage exceeding the 0.7 volts, even without an R-sense resistor. This timer feature can be exploited as it prevents the circuit from being left on for too long. Give it a try. It will be a good challenge for you. And at the end, you will have the satisfaction of achieving something very different. As you can see by the picture, I have got a collection of circuit breakers, from part 1 to part 5 videos, each one with a different current limit. I use them to protect against high current, or short circuits, when doing breadboard testing for new projects. And that's all, folks. I hope you enjoyed the video. And I thank you all for watching. Thank you.